Hello and welcome to this example of using equations of state to do a more realistic process calculation. And so what we're looking at here is an ammonia plant. So this is the flow sheet that I've been using in a few examples. And what we're looking at in particular is the chiller section of this process, where what we need to do is to cool ammonia down to 250 Kelvin or minus 23 degrees Celsius so that it liquefies for storage. Now, to get down to these sorts of temperatures, we can't use air and we can't use cooling water as we would often use on a process plant to do cooling. So we need a refrigeration system to do that work for us. And a sensible choice would be to use an ammonia-based refrigeration system, seeing as how you're on an ammonia plant and you have lots of ammonia lying around. Now here we have a typical refrigeration cycle. So we have a compressor, which is the thing that we're interested in, and then after the compressor we've got our condenser, our expansion valve, and then we're actually cooling the process stream in the evaporator of the refrigeration cycle. Now in this compressor here, we're compressing gases from 1 bar all the way up to 16 bar. Now, to increase the pressure by that amount, it's actually difficult, impossible to do in a single stage. So what we have instead is a multiple stage compressor, where we have our gas coming in at 1 bar, and then it goes through 1 compression stage, 2 compression stages, 3 compression stages, 4 compression stages, until it comes out at 16 bar. In between, we've got cooling happening. Okay, so because this improves the energy efficiency of the compressor. And then what we're specifically going to be interested in here is this final stage. Okay, so here's our system boundary, and what the gas is coming in at. Okay, so in here it's coming in at 8 megapascals and at 310 Kelvin, and it's coming out here at 16 megapascals, not bar, sorry. But we don't know what temperature it's coming out at, but we do know what the isentropic efficiency is of this stage, and it's 70% or 0.7. So we're going to figure out the energy consumption of this stage. Okay, so the amount of work per mole of flow. To do this, of course, so we're wanting to figure out the amount of energy, we need to make assumptions about the system. So steady state, pure ammonia, and no heat loss. And because we're interested in work and energy, we need to use the first law. Now I'm missing a few dots here, so that's flow, that's flow, that's flow, and that's flow. There, now it's steady state, so all my time-dependent terms disappear. There's no heat loss, so this disappears. So what this gives me then is that my shaft work per unit of molar flow is equal to my enthalpy in minus my enthalpy out. Okay, so I'm wanting to calculate the change in enthalpy between my inlet conditions. Okay, so I know my T in and I know my P in, I know my P out, but I don't know my T out. Okay, so that is a question mark. So to be able to get my work and to find out what that temperature is, I need to start from a basis, and that basis is that I'm going to look at the case of an isentropic compressor. Okay, so I'm going to set my entropy change equal to 0. Once I've got that, what that gives me then is my reversible work. From this, I can get my real work required as being equal to my reversible divided by my efficiency, and from my real work I can get my H in minus H out, and I can get my temperature out. Okay, so this is a multi-step process, and so we're familiar with this process from having done these types of calculations using tables, but we're wanting to do this calculation now using equations of state instead. So we'll start by looking at how we're going to calculate delta S using our equation of state, and the equation of state that we're going to use is the Peng-Robinson equation of state. Okay, so now that I know my initial task is to calculate the entropy of the compressor, then I start with listing what I know. So I've got the Peng-Robinson equation of state here. So these are all the parameters that go into it. And so I'm wanting to find where delta S is equal to 0. So delta S is just simply the difference in the entropy between the outlet conditions and the inlet conditions. And so as per the previous couple of lectures, I can group this together into its ideal contribution to the change, and then also the departure contributions to the change. So expanding out on these, so I've got the ideal gas contribution here, so which we've calculated previously, and then I've got the departure entropy at the outlet conditions, and then the departure entropy at the inlet conditions. Okay, so to be able to do this, then I need to go through a few steps. Okay, so the steps that I'm going to go through here, so I already know my my inlet conditions. So the first thing I'm going to do is solve for the inlet volume at T1 and P1. Okay, now I don't know what the outlet temperature is, so I need to guess what T2 is. Okay, and so my initial guess is it's going to be something greater than T1. Once I've guessed what T2 is, then I can solve for the volume at the outlet at T2 and then P2, which I know, so I'm not guessing that. Once I've got my volumes, okay, then I can calculate my S departure. So at T1 and P1, I can calculate my S departure at T2 and P2, and then I can calculate my delta S star. Now that I know the temperature, I can calculate the temperature contribution to the change, and then I can sum these together. So my delta S is equal to delta S star plus my departure at the outlet conditions minus my departure at the inlet conditions. So this is just 1, this is 2 here. Then my final step is to say, okay, so is delta S equal to 0? So if the answer is yes, then I've found the reversible outlet temperature. If the answer is no, then I'm going back and refining my guess. Okay, so you keep changing your guess or estimate for the outlet temperature until the change in entropy is equal to 0.